Hey, welcome back to graph theory. In this lecture, we're going to take a, kind of gentle introduction to the notion of planar graphs. It's discussed in section 9.1, and we'll kind of break the material up. So today, you can see the goals there. We're just going to try to motivate what the notion is of planarity, try to give a definition of planar, and everything that I'm saying here is good for graphs and multigraphs, and it's kind of interesting in some applications. So we'll go ahead and give proofs that are valid for multigraphs as well. We're going to state and prove something called Euler's formula, which is something you may have seen before about planar graphs, but it's also very interesting. And along the way, we'll illustrate with lots of examples. All right, so let's just get started. Try to keep this video as short as possible, and you can come to class if you want to discuss it in real time. So here's the motivation. This is a classic example. Every time I've ever seen anybody talking about planarity, they motivate it with this example. So you have three households and they need three utility services, say water, electricity, gas, whatever utility services you like. And then this simple model, we're going to run services in with lines underground. And of course, they're all at the exact same depth. So we're trying to make sure that no two service lines cross, except for, of course, where they originate and where they terminate. All right. So you can see I'm modeling it with a graph down there, a bipartite graph. I'll let vertices be houses and services be the other vertex set. Those are the parts. And then I'll draw an edge for a service line. So for example, house one needs water. Okay, well, we'll give house one water. House one needs an edge, or sorry, electricity. House one needs gas. No problem. Remember, we're trying to get these things not to cross. So house two needs water, but there's no trouble. We'll just run that kind of funny looking line there. And house two needs electricity. It's also no trouble. We can do it. House two needs gas. There's lots of ways, but look, that's the easiest way to go. And house three needs these things. House three needs gas. It's not a problem. House three needs electricity. It's not a problem. And house three needs water. And now it seems like we have a problem because to get house three to get water, well, maybe there's some way to do it. I made choices along the way. You can stop the video, solve the problem. But so far I haven't solved it. I'm just going to indicate that. So we're going to call, what I'm trying to do is I'm trying to draw the graph K33. I mean, maybe I should say that. So that's kind of a restatement of this problem. This problem is saying draw the complete bipartite graph K33 with no crossings. What's a crossing, you say? Well, a crossing in a graph, a multigraph more generally, it depends on a drawing. So we're kind of bringing in some topology, some geometry here. A crossing in a drawing of a graph, we draw it in the XY plane, a two-dimensional plane. It's a point in that plane that's on two edges, but it's not a vertex. Yeah, so that's what I was trying to avoid up here. I was trying to avoid the service lines crossing. Here's what a crossing looks like in a graph. We'll denote vertices like we usually do, open circles. And this graph has a crossing right there. There's a point on those two edges, but that point's not a vertex. All right, so we're going to call a graph planar if you can draw it with no crossings. If you can draw the graph with no crossings, then we're going to call it planar. Look, I'm showing you the first three complete graphs are all planar. Right? K1 doesn't have any edges at all. K2, no crossings. K3, no crossings. K4, well, in this drawing, I've got a crossing. But it's possible to redraw K4. You can probably see pretty quickly. We don't have to draw lines as straight edges, although there's actually a theorem that says you always can if you have a planar graph. But we can connect these last two vertices like that, for example. That's also a rendering of K4. It's not very symmetric. I personally like this rendering of K4. You draw a K3, sort of a wheel graph, yeah, a wheel with a cycle. Or actually, sorry, that's just, yeah, this is just K4. What would we call it? W13. That's the wheel with three spokes. Cool. So I'm going to postpone it till next time. The author of the book, I'm not doing this quite in the same order, but we're going to show, among other things, that K5 is not a planar graph. Neither is K33. If you're still working on that puzzle while I'm talking, that puzzle up there is impossible. You're not going to be able to connect house 3 with water without a line crossing, because K33 is not a planar graph. We'll talk about this next time. We won't prove all of the things that we're going to say, but we'll give a characterization of planar graphs next time. But I'm gonna leave that as this sort of suspenseful moment, and you'll come back. This is just some more vocabulary. The crossing number nu of G, that's the Greek letter nu. If you want to say V, it's okay with me. Is the number of crossings in a minimal crossing drawing of G. All right. So of all the drawings of G, there's some number of crossings. There has to be some a least number because they're bounded below by 0. So whatever that least number of crossings is, we're going to call that the crossing number. Okay. A graph is planar if and only if it's crossing number 0. You can draw with no crossings at all. I'm going to prove to you in Wednesday that the crossing number of K5 and K33 is 1. Those graphs aren't planar, but they do have crossing number 1. All right. In some sense, the crossing number measures how far away. If you have a huge crossing number, you're really not planar. Cool. Okay, we'll talk about those characterizations next time. To get at this Euler's formula, I need to borrow a little theorem from topology, or just if that's not a familiar term. I mean, I'm going to assume some fact, and the fact will actually seem quite obvious. But as in many things in geometry and topology, the more obvious the statement sounds, usually the harder it is to prove. But so you can just check this away in the realm of obviousness. But really, there's something deeply geometric here about the plane. So what is this fact that I want to borrow? It's called the Jordan curve theorem. And it says that if you take a simple closed curve in the plane R2, so that's a lot of technical words. Simple closed curve, I'm just going to kind of give you a little vocab here. A simple curve means it never does that. It never crosses itself. All right. So if you have a simple closed curve, that's forbidden. I like this one over to the left. It's simple. Just keep looking at it as an example of something that is this. I'm going to draw stuff over here. So simple means no crossings. Closed, well, no crossings except for, yeah, so closed means that the initial and terminal points are the same. Okay, I'm saying this, I'm not writing it very clearly, but a closed curve means that it has some initial point, and that initial point is equal to the end point, the terminal point. Okay, so a simple closed curve you might think is a contradiction. Well, the curve is still simple if it only intersects itself at that one and only point. All right. It's a simple closed curve. I should have said this at the beginning, but this is kind of a generalization of a circle. It's like a warped circle. So you can't make it cross over on itself. You can't break it so that it doesn't end where it started. And that's it. It's a simple closed curve in the plane. And then what the Jordan curves theorem says is that its complement, R2, take away that curve, all the points in the plane that aren't on the curve, it has two pieces. It has two connected components. A connected component in the plane means that, here I mean path connected. If you pick any 2 points in there, if I pick any 2 points inside, that's one of the components' names, I think it's a good name, then you can draw a path between those two things that stays inside. Yeah, any 2 points. Even if you pick one over here and one up there, I can draw a path, stays inside between them. Same for the outside. Pick any 2 points outside, that's the other component. You can draw a path between them that stays in the outside. But if you pick a point inside and outside, you can't draw a path between those 2 points that stays in the complement. Yeah, like I'm not allowed to leave the, I'm not allowed to leave the complement. I'm not allowed to cross the curve gamma. So there's two connected components. So that's all the Jordan curve theorem says. You draw a simple closed curve in the plane, it cuts the plane into 2 pieces, the piece that's inside, the piece that's outside. All right, I think that's interesting. I'm not going to use it in some formal way. I wanted you to bring it up. It's a famous theorem. It's a good thing. You're getting a mathematics education. You should hear about these theorems. If you take a topology class sometime here at HSU, we certainly don't offer one regularly, but it's been done as special studies before. Then you can kind of look at some of the nitty gritties of like how does somebody prove something like that? This obvious sounding fact. I mean, it's said an earlier way, you draw some curve in the plane that doesn't cross itself and closes back up, but then you enclose some region, okay? And that's its inside. What's out there is outside. Well, how I want to use it is that if you give me a planar drawing of a plane graph, right, then it divides the plane into these regions called faces. And I'm not going to get into the details of this, but if you start at some vertex and kind of start looking around for some closed walk, then that's a sort of the same thing as a simple closed curve in the plane, and that's got an inside and an outside. Yeah, and all of these walks have that, and those are the faces of the graph. One of the faces is unbounded. The outside face, we'll call it, unbounded in the sense that there are points in it that are arbitrarily far away from your vertices and your vertices in your graph. But we always count them like that. So if we look at this graph that I've drawn here, K4, its order, the number of vertices is 4. It's also its size, and the number of its faces, let me enumerate them. There's 1, 2, 3, and the outside one makes 4. All right. Sorry, let me back up. I'm not gonna I'm not gonna re-edit this video. I'll just eat my shame publicly here. But the size is 6. Pardon me. It has 6 edges. It doesn't have 4 edges. I was talking too fast here. There's 1, 2, 3 right there, and 1, 2, 3, 4, 3 more right there, and 3 plus 3 is always 6. Okay, good. So this is sort of a random thing to do, but look, if we take the number of vertices, the order, and we subtract the size, and we add the number of faces, we get 2. Cool. We'll talk about this in the Zoom class if you want to come. I'm going to be try to sort of brief about it here because you can just sort of Google and read on your own. But these things are called the planar graphs of the so-called 5 Platonic solids. You can model these things. You can take triangles and regular pentagons, squares, and assemble these things into 3-dimensional figures. These are sort of planar projections of them, but we can just look at them as graphs. They're all planar graphs. None of those graphs have crossings, and they have these kind of interesting Greek names: the tetrahedra, the octahedra, the dodecahedra, the cube, and the icosahedron. And I would just like to do that same calculation. We just did the tetrahedron up here. The tetrahedron is just K4, and it was the 4, 6, 4, and 4 minus 6 plus 4 was 2. Let's do the cube. The cube has 1, 2, 3, 4, 5, 6, 7, 8 vertices. It has order 8. And don't trust me, you should stop the video and count yourself, but how many edges does it have? It looks like it has 4, 8, plus 4 more, 12 edges. And then how many faces? Well, have you ever rolled a die? Think of the 3D version of this thing, and the number of faces is easier to think about. There's 6 of them. There's these 4 faces. There's this one that's the innermost, and then never forget the outer face, the unbounded face. So if we take, in this case, 8 minus 12 plus 6, we again get 2. I'm going to leave it to you. You'll have to sort of stop the video and do this for a while, but each one of these things has an N and an E and an F. And I'd like you to compute it, but plot spoiler, I'm going to tell you every time you do that the N's and the Q's, the N's and the Q's are going to be, I keep writing E where I meant Q, they're going to be different in all of these examples, but this quantity N minus Q plus F, it's always going to be 2. It's always going to be 2. So that's how we're going to, let's try this in a multigraph. I want to try it in a multigraph because I said this stuff is all valid there. Here I've drawn just K3, but let me jazz it up for you a little bit. Let me put in some multi-edges. I'm going to draw something that looks like this. You can even put in loops, right? So in these multigraphs, I'm allowing loops. And now let's count. I didn't change the number of vertices. I did the edges. How many are there? There's, let me do it like this. There's 1, 2, 3 of those first ones, 4, 5, 6, and then 7, 8, 9. That's how you count the loops. The loops are an edge. So in a multigraph, that has size 9. And then what about the faces? There's, I shouldn't draw my vertices here. You got to remember, those things aren't loops. So the faces, what are there? There's 1, 2, 3 inside those little loops. There's the outer face, 4. There's this inner one, 5, 6, 7, 8. It looks like it has 8 faces. Yeah, and you can check 3 minus 9 plus 8. Check it out. Don't trust me. It's 2. Cool. All right. So let's try to prove a theorem. The theorem is if you have a connected planar drawing of a planar, multigraph, and to keep this video short, I'm not quantifying all of this stuff carefully. Forgive me for being so sloppy in my mathematics. But the order minus the size plus the number of faces is always 2. Leonard Euler noticed this. Of course he did. Let's check out a proof. I'm going to, my proof's a little different than what's in our book because I'm doing it for multigraphs, but in essence, it's the exact same idea. Okay, so we're going to induct on the order. So if you have just one vertex, then your multigraph is just a bunch of loops. People call it a bouquet of loops. If you have just one vertex, you might have no edges, 1 edge, 2 edge, but you can draw it like that. It's a bouquet of loops, a planar multigraph with just one vertex. So if you don't have any edges, well, then you have one face. Yeah, I could draw that over here. Here's a multigraph with no edges, and it has exactly one face. It's out there. And you can check the formula works. If you take 1, take away 0, plus 1, you get 2. I'll let you check that out. So the Jordan curve theorem says that every time we add an edge to this graph over here, pretend I just added a red edge, you split the existing face that the edge is drawn in into 2, right? So this new thing has 2. And if I added another edge, well, I just split that outer face into 2, this piece and this piece, and so on. So every time you add an edge, you end up adding a face because you've taken the face that you're drawing the edge in and making it into 2 faces, right? So what that means is that both Q and F increase by 1. So in this expression, that expression is going to be a constant. If you increase this quantity by 1, it's got a minus sign in front of it, but you pay for it by increasing that quantity by 1. So it's never going to change, right? So for in this case where n is 1, as you click up q, that stays constant. It'll always stay equal to 2. So that proves the base case. So now let's suppose that Euler's formula is good for any connected multigraph, planar drawing of a planar multigraph where the order is at least n, or excuse me, is equal to n. N is some number that's at least 1, is what I meant. I'm trying to talk too fast. And then give me such a graph, I'm not even going to try to say it again, that has order n plus 1. Give me a planar connected multigraph of order 1 more, okay? What do I have to do? I have to prove that Euler's formula works for it. Good. So it has at least 2 vertices because we took care of the case where we had order 1, right? So we know that if there's one vertex, how it all works. So without loss of generality, we can assume, well, sorry, what am I talking about? N is at least 1, so n plus 1 is at least 2. And it's a connected graph. So it can't just have loops. Okay, G can't just have loops because if it just had loops, it wouldn't be connected. So there has to be some pair of vertices in the graph, I won't even give them names, that have an edge between them that's not a loop, like that. And in a planar graph, every edge has exactly 2 faces, one on either side of it. Each edge is kind of incident with, you can say, 2 faces. And these vertices might have other edges. Some of them might even come together at vertices, like that. You know, but the edge E is incident to these 2 faces, F1 and F2. So then the construction is I'm going to so-called contract that edge. I'm going to contract the edge E into a single vertex. So what do I mean by that? I mean, take the vertex that's the vertices on the edge E and bring them together into one vertex. So you're getting rid of that edge. Okay, all of the other edges incident with those vertices remain intact. They don't change in the graph. And for that matter, the number of faces doesn't change because this edge E, when you bring it together and make it a single vertex, the faces F1 and F2 are still there in the new graph, G prime, after this contraction, and so are all the other faces. All right, so in this new graph, the number of its vertices is 1 less. Remember, G had order n plus 1. We've reduced the number of edges by 1, and we didn't change the number of vertices at all, or faces at all. So by induction, right, because G prime has order n, by induction, Euler's formula holds for G prime. N prime minus Q prime plus F prime is 2. So if we make the substitutions, right, N prime is N, Q prime is Q minus 1, do a little bit of algebra, that minus a minus 1 is N plus 1, but that's the order of G. So the order of G minus its number of edges plus its number of faces is 2. And so therefore, Euler's formula holds for the graph G, and by induction, it holds for all multigraphs. All right, so thanks for listening.